Hi, my name is Adrian Marotzke. I'm a PhD student at the Hamburg University of Technology and NXP Semiconductors. And since October, I'm also part of the submission team of NTRU Prime. And today I would like to give a presentation about my paper titled A Constant-Time Hardware Implementation of Streamlined NTRU Prime. Short agenda, I will begin with an introduction to what is Streamlined NTRU Prime. Then this will be followed by a description of the algorithm, followed by an overview of my implementation, which in turn will be followed with a key highlights of the implementation, so details that are of interest. And finally, there will be a conclusion and an outlook for future work. What is Streamlined NTRU Prime? Streamlined NTRU Prime is one of the alternate finalists of round 3 of the NIST post-quantum cryptography standardization process. It is a lattice-based key encapsulation mechanism, and it has its ancestry in the original NTRU scheme from 1998. However, there are several improvements. And these improvements are all about reducing the attack surface at low cost. So for one, Streamlined NTRU Prime does not have decryption failures. So every ciphertext is always correctly decrypted. And this is achieved by the fact that there is no Gaussian sampling. Instead, the ciphertexts are rounded, and the use of fixed weight secrets. There are also Streamlined NTRU Prime does not use cyclotomic rings. Instead, rings of the form called RQ and R3 of the form ZQ with the irreducible polynomial x to the power of p minus x minus 1. And both p and q are prime numbers. Finally, Streamlined NTRU Prime also uses a key confirmation hash, which is appended to the ciphertext. And this is a hash of the public key and the secret input. And this is done in order to simplify the security analysis of the algorithm. Some definitions. A polynomial where all coefficients are either -1, 0, or 1 are called small polynomials. Polynomials that polynomials have weight w if exactly w coefficients are non-zero. And polynomials are called short if they are both small and have weight w. We will use hash a of x to denote that this is the SHA-512 hash of x prefixed by the single byte value a. And encode and decode functions this is simply a transformation of field elements to byte strings and vice versa. Below, you can see the round 2 parameter sets with values for p, q, and w, as well as the corresponding security strengths. All numbers in this presentation will refer to the p equals 761 parameter set. So I will now go on and do an overview and description of the algorithm itself, beginning with the key generation. So this starts off that we generate a uniformly random small g, as well as the short polynomial f. We then proceed to invert these polynomials, 1 over g in R3 and 1 over 3f in RQ. We then take our 1 over 3f polynomial and multiply it by g in RQ to get the polynomial h. We then encode this polynomial to get the public key. Afterwards, we then hash the entire encoded public key to get the public key hash. We also generate row as a row is a random byte string of a specific length. And finally, all these values, so row, the 1 over g, short f, the coded public key, and the public key hash are all concatenated to create the private key. This is the entire key generation process. For the encapsulation, we of course first have to have a public key, and then we generate a short polynomial called R. This R is then multiplied with the polynomial H in RQ. We then take the resulting polynomial and round each individual coefficient to the nearest multiple of 3, and then call this polynomial C. After that, we first again hash the encoded public key to get the public key hash. And we also encode the short polynomial R and hash that to get R hash. These two hash values are then concatenated and hashed once again to create the confirmation hash. Then we take the polynomial C, encode it into a bystring, append the confirmation hash to generate the ciphertext C. And then to generate the shared secret, we take the value of R hash, append the entire ciphertext, hash it one final time, and then we have our shared secret. That concludes the encapsulation. The decapsulation, of course, we have the private key and a ciphertext, which we receive. We first take the polynomial C and F and multiply them, and multiply that again by 3 in RQ. We then take of this resulting polynomial, we take each individual coefficient modulus 3 to obtain the polynomial E, which is then in R3. We then multiply the polynomial E with the 1 over G from the private key, obtaining the polynomial R dash in R3. We then have to check whether or not R dash has weight W. If R dash does not have weight W, we set the first W coefficients to 1 and the rest to 0. If R dash does have weight W, we leave it as it is. We then redo the encapsulation process with the public key H, but instead of generating a new short R, we use the R dash, which we just calculated. From this encapsulation process, we then get a new ciphertext called C dash, which we then compare to the original ciphertext we received in the beginning. If these are equivalent, then we output the hash of the encoded R dash appended with the ciphertext and one hash once again. This is the same as from the encapsulation process. However, if C does not equal C dash, then we replace the encoded R dash with the value rho and hash that to obtain a pseudorandom value. Okay, and this is the entire process. These are the three main parts of Streamlined NTRU Prime. I'll now go into a little bit of an overview of the implementation. So as mentioned in the title of this presentation, it is a hardware implementation of Streamlined NTRU Prime. It is written in VHDL, and all operations are supported. So key generation, encapsulation, decapsulation, as well as all necessary encoding, decoding, and submodules and subfunctions, as well as all round 2 parameter sets. Now, this implementation is designed for small embedded systems, such as smart cards or other lightweight systems. And the source code is available in the linked GitHub repository under an MIT license. Some benchmark numbers. This is for the parameter set P equals 761 and on a Xilinx Zynq FPGA. So key generation takes just over 1.3 million cycles. Encapsulation takes just over 142,000 cycles, and decapsulation takes just shy of 260,000 cycles, with a max clock frequency of 269 megahertz. Since the paper was submitted, there's been some improvements, or some fairly significant actually improvements to the algorithm, hence both the numbers original from the paper as well as the current ones. And the current ones currently need just shy of 1,600 slices of the FPGA, together with 13 block BRAMs and 19 of the digital signal processors. So now I'd like to highlight some of the details of the implementation that are noteworthy. So for one, the inversion. So during the key generation, we have to invert two polynomials, one in R2 and one in R3. And for this, the extended GCD algorithm is used. This algorithm was presented by Bernstein and Yang at CHESS last year. And this algorithm is significantly faster than other constant time inversions, such as Fermat's little theorem. Nevertheless, the key generation cycle count is dominated by the time it takes to invert these polynomials. Almost 90% of those 1 million cycles is needed by the inversion. With multiplication, there's also the interesting fact that due to the design of the ring, so this x to the power of p minus x minus 1, using NTT is not straightforward. It is not impossible. It is just significantly more difficult than in other lattice schemes, and this is also why pretty much all other lattice schemes which use NTT for fast polynomial multiplications. But in NTRU Prime, this is not simply done. So instead, I use a mixture of Karatsuba and Skubal multiplication. And this actually achieves decent performance. So even with just one layer of Karatsuba multiplication, multiplication takes just over 78,000 cycles. An interesting thing here is that we never multiply two polynomials in R2. One of the polynomials is always in R3. So yeah, we are multiplying one with one in R2 and one in R3. And this means that the coefficients are for the one polynomial are 13-bit, but from the other are only 2-bit. And in fact, are not only 2-bit, but are only -1, 0, and 1. And multiplying a 13-bit element by -1, 0, 1 is essentially nothing. And as a result, the Skubal multiplication is very resource-light because we don't have to do full like 13-bit times 13-bit multiplication and then do a big modulo operation afterwards. And this saves significant resources. When we have to multiply two elements in R3, this is done actually by the very same circuit. Just at the end, we do right at the end, we do a modulo 3 at the end to ensure that the polynomial is still in R3. But otherwise, the operation is identical. About generating short polynomials. These polynomials, of course, have to have exactly weight W. However, this is not done with sampling, such as rejection sampling. And instead, we take p 32-bit random numbers, random integers, and of the first W integers, we modify the last 2 bits so that they are always even. And of the rest, we modify the last 2 bits so that they are always odd. We then sort this large integer array with a constant time sorting algorithm. And when I say constant time here, I of course mean that no matter what we input, it always takes the exact same number of cycles. For this, I used the sorting network that was presented in the original NTRU Prime paper. And this can sort this array, for example, for when p equals 761 in 50,927 cycles. After sorting, we simply throw away the upper 30 bits and only keep the last 2 bits and subtract those 2 bits by 1. And then we have our nice, shiny, short polynomial with exactly W non-zero coefficients. And a little bit about the encoding and decoding. Both encoding and decoding in R3 is trivial. These are 2-bit coefficients. We can simply pack them in a shift register and then output bytes. It is trivial. For the RQ encoder, it's a bit more complicated, but we can do this is done with a mixture of bit shifts, 16-bit additions, and 16-bit multiplications, so still nothing too fancy. For the RQ decoder, however, this requires a 32/16 division operation with remainder. However, we do not have to do a full division circuit. Instead, and this is because all of the divisors can be pre-calculated. There are 42 divisors in total per parameter set, and these can all be pre-calculated. And this means that we can replace the division operation by division by a constant, which in turn can then be replaced by a multiplication and a bit shift. An important thing to note here is that these divisors are not secret dependent. They are simply predetermined by P, Q, and W. So there's no side channel risk here. Below you can see an example for division by 4,591. We take the value of x which we want to divide, multiply it with this big integer, do a bit shift, and then we're done. And this is valid for all values of x that are between 0 and to the power of 32. To get the remainder, we simply multiply the result by 4,591, subtract that from x, and then we have our remainder. About the hashing. So the actual time spent on hashing is actually very short. Only 325 cycles are needed per 1024-bit block. And the actual total time of the entire algorithm that is spent on hashing is only under 0.5% for example, for the decapsulation. However, the SHA-512 module used to be actually the single largest module. This is one of the areas that have been optimized since the paper was submitted. And now it is only one of the largest modules, but it still uses a significant amount of the resources. And so a big takeaway is that finding the optimal sized SHA-512 implementation is critical if you want your design to be as resource efficient as possible. And there's of course a big bonus if your crypto coprocessor or embedded system or whatever already has a SHA-512 implementation, because that means adding Streamlined NTRU Prime will cost nowhere near as many resources as if you would have to include the additional SHA-512 implementation. A little bit about the constant time in this. So yeah, as mentioned, every single operation in the design is constant time. The sorting allows also the constant time generation of these short polynomials with a fixed weight. Also special care, of course, was taken to the two places during the decapsulation. So for one, where the polynomial r dash is checked if it has W non-zero coefficients. This is very important, of course, that this is done in constant time so as not to reveal information on the value of r dash. And of course, also the cipher equivalence check after the re-encapsulation. So where we check the original ciphertext with our newly generated ciphertext. This is also done completely in constant time, again, so as to not reveal any information of the result of this check. The little thing in general about Streamlined NTRU Prime is, of course, that because there are no decryption failures ever, there cannot be any side channel attacks that exploit decryption failures, simply because there are no decryption failures. So that's one benefit. That being all said, this design does not have any advanced protections against more complex side channel attacks, such as differential power analysis or fault injections. These are not present. So to my knowledge, this is the first full implementation of Streamlined NTRU Prime. There was a published design that did not have key generation or decoding implemented in hardware, only encapsulation and decapsulation. So yeah, to make this comparison fair, I wrote from my design, these numbers in the second line, you can see the numbers from my design without the key generation or the decoding part. And we can see that while the other design is significantly faster, so basically an order of magnitude faster compared to my design, it is also an order of magnitude more expensive. So in comparison to the 1028 slices that my design uses, this other one needs over 10,000. So we get that, yeah, it is an order of magnitude faster, but also order of magnitude slower. If we look at the throughput per slice, so to say, it is actually somewhat equivalent. So finally, I will then go to do a conclusion, as also talk a bit about some future work that can still be done. So yeah, as a conclusion, we can say that a lightweight implementation of Streamlined NTRU Prime is very much possible. and this is suitable for embedded systems and without too large of a performance penalty, which of course is nice. As for future work, of course, for one, with the start of round 3, there have been several additional parameter sets have been included in Streamlined NTRU Prime. The round 2 parameter sets are still valid, so this entire thing can still be used as is, but of course the new parameter sets have to be added. In particular, for the decoder, the divisors have to be pre-calculated and added. Then, despite some significant improvements on the SHA-512 implementation, I do not think it is actually really, it is not optimal yet. So there's still potential for significant savings or resource savings there to find really the optimal SHA-512 implementation. As well as, of course, adding more advanced side channel protection. So as this is intended for embedded systems such as smart cards, these would, of course, require advanced side channel protections against, for instance, differential power analysis. This could be in the form of, for instance, masking. Then, of course, a study of whether or not the number theoretic transform used for multiplication would, the research of its suitability would, of course, also be interesting. So while it is much more complex than the multiplication I use right now or how the entity is implemented in other schemes, it is still worth researching whether or not the complexity is worth the performance boost which would obtain by using an entity multiplication. Finally, there is something about the key generation which can also be used, and that is to do a batch inversion using Montgomery's trick. Montgomery's trick allows us to replace n inversions with n inversions with one inversion and a certain number of multiplications. And this would mean that if we generate batches of public-private key pairs, we would only have to do one inversion and a whole bunch of multiplications. And this would, of course, mean that the one super expensive inversion can be amortized across several public-private key pairs, significantly improving performance. Of course, this would also, you would have to check whether or not the additional memory requirements, which we, of course, need to do this entire batch processing, how expensive that would be. Yeah, with that, I conclude my presentation. Thank you very much for listening, and have a nice day.